So a few weeks back, a colleague of mine on the EBS team told me a story about when he first moved to Seattle. Now, he decided that he wanted to get a bike to commute to and from work. And for those of you that have never visited Seattle, Seattle has some hills, and those hills make San Francisco streets look tame. So anyway, he buys this bike, and he tries to commute home. Unfortunately, he doesn't even make it all the way home. He has to get off his bike and walk. Come to find out, he's only ever ridden a single-speed bike, and he didn't realize how to use the gears on his new bike. Once he figured out the gears, he was able to climb hills. I'm Mark, and I'm a software engineer on the EBS team, and I've been focusing on the core I/O path with EBS for the last 4 years. Now, my goal today is that by the end of the talk, you'll know a few more tips and tricks that will help you improve the performance of your application, much like my colleague learned how to use his bike. So how many people are returning after Dougal's talk? Well, a good number of people and some new faces. That's great. So for those of you that are just joining, I'm going to spend a few minutes to recap what Dougal just talked about and go over an overview of what EBS is. So Amazon EBS is block storage for EC2. Now, we look like a block device to your instance, but it's important to remember that EBS is not just a bunch of disks. So what is EBS? EBS is Persistent Network Block Storage as a Service. Now, the service part of that's really cool. It means that we can iterate and improve the performance and improve the feature set on EBS without you having to do anything. Now, EBS is also a zonal service. And that means that once your volume is created, all of the resources for your volume live within a single availability zone. And that volume can be attached to any instance in that availability zone. So EBS has other features such as snapshots and encryption, designed for 5 nines of availability, and we create over 2 million volumes every day. EBS has a few different volume types. EBS magnetic, which is the original volume type, and 2 SSD-backed volume types, general purpose volumes, or GP2, and provision IOPS volumes, which we refer to as PIOPS. So EBS magnetic volumes. These are best for infrequently accessed data. So say you take a snapshot of your database. You can stuff that snapshot onto the magnetic drive so that it's next to your instance in case you need it quickly. It's also good for log storage, so application logs and system logs and other things like that. And if you have cost-sensitive workloads, magnetic's still a good choice for you. Now, GP2 volumes. I'm not going to go through all of the slides that Dougal did to explain GP2 volumes, but the bottom line with GP2 volumes is that they just work. We've designed these to be applicable to most workloads, and they have an IOPS baseline that's up to 10,000 gigabytes, and that is allocated based on the size of your volume. GP2 volumes also, for smaller volumes, have a burst bucket. And this burst bucket allows you to drive 3,000 IOPS for up to 30 minutes. And now when you're not driving that 3,000 IOPS, that bucket continuously refills at your baseline rate. So it's a little confusing with the burst bucket, but really, I don't want you to have to think about that. These just work. And in fact, they work so well that most of our GP2 volumes don't even come close to exhausting their burst bucket. Now, for your mission-critical workloads, those are your critical production database that can't even tolerate a stall on a select, things like that. We recommend provision IOPS volumes. Now, these can be provisioned up to 20,000 IOPS, and those IOPS are independent of the size of the volume. These also have a higher throughput and a higher performance consistency. So now let's jump into why you're all here. But before we get started, let's talk about a little theory. So John Little is a professor, and he spent most of his research focusing on operations. And in the 50s and 60s, he was thinking about EBS. Wait, that's a lie. He was thinking about a bank. It turns out that his research then was actually still applicable to EBS. And he proposed a theorem. And that theorem seems obvious now that it's on paper, but nobody had really thought about it. And it's that the wait time of a request, in his case, the patron's waiting to do transactions, is equal to the queue length divided by the arrival rate. And so this is exactly how EBS works, and this is exactly how most systems work. Now, it's also important to note that these three values, as they pertain to EBS, are available as CloudWatch metrics, and we'll talk a little bit more about that later. So when we talk about performance optimization, we look at these three things. There are a few other things, but these are the core things that we think about. The IOPS, or the rate of I/O that is going to your volume, the latency, which is the time that those IOPS take to complete, and the throughput. Now, your database workloads are going to be focused mainly on IOPS and latency. Your streaming, video streaming, log processing, Splunk, Kafka, things like that are more concerned about throughput workloads. So to achieve end-to-end performance optimization, you need to look at these four components. For many of you, this is going to be a review. But let's make sure everybody's on the same page. You have your EC2 instance. That's where your application is running. Your application is submitting I/O, and that I/O is targeted at an EBS volume. To get to that EBS volume, there needs to be a network link in play. And these four key components work together. So to maximize performance, it's important to arrange them into a balanced system. Let's start by looking at the I/O component. All right, I'll admit I'm a little bit of a scuba diver, so I used a dive slide because we're going to go on a deep dive into the kernel. Now, a lot of you have focused on storage optimization, but your focus has been on on-premise systems. Getting an I/O to the storage layer in a virtualized system is a little bit different. And so I thought it would be important to take some time to explain how that happens. So you have your instance. Your instance is running an application. Your application wants to do an I/O. That could be a read or a write. Could be written in Java or assembly, doesn't matter. Eventually, that read gets converted into a system call into the kernel within your instance. Along with that system call is a buffer, and that buffer is where the data goes. Now, if it's a read, the EBS volume will put the data there. If it's a write, that's the data that's going to get recorded on your EBS volume. And so the kernel knows that it's not talking to a real block device underneath. It's talking to virtualized storage. And so it contacts an I/O domain. Now, for every EC2 instance, it has a communication path with an I/O domain. And that I/O domain has all the software that directly accesses the EBS volume. The problem is that I/O domain doesn't have access to your instance's memory. And so the instance has to alert the I/O domain and say, I'm going to grant you permission to this piece of memory. And that process is called a grant mapping. And now this process is actually really fast and pretty neat. It's fast for bulk data transfers, but it can be a little bit costly from a CPU perspective because every time you do one of these, it requires at least one TLB flush as we switch back and forth between the guest instance, your EC2 instance, and the I/O domain. So once we've got that I/O mapped, now your instance is able to create a request. And that request looks a little bit differently, a little bit different from a normal block I/O request. But really, it's about the same. It has the location that you want to read from or write from, the amount of data that you want to read, and a bunch, 11 to be more specific, slots for these grant mappings. Now that instance communicates with the I/O domain for these requests through a single memory page that is mapped, and that your instance and I/O domain have access to. It's treated as a circular queue, a ring buffer. And ring buffers, as some of you probably are familiar with, are most efficient when every request is the same size. And so you're probably thinking, why only 11 grant references? Well, it turns out that if we add a 12th grant reference in there, we can't fit 32 IOs into the queue. And we want that queue to be base 2, and we want to have a large enough queue that you can submit enough IO. The problem is, this only is just under 1.5 meg of data. So it's not a whole lot of data that can be outstanding. And if you're submitting larger IOs, they'll get split down into 44K. So the 3.8 kernel in Linux included a number of features. And so if you remember, I was talking about the TLB flushes before. If you're trying to do a lot of IO, your instance is going to try and submit an IO. We have to do a TLB flush. IO domain has to do that grant mapping, may do a TLB flush on the way out, and then when the IO is done, we'll have to repeat the process again. And so the CPU is doing a lot of extra work. It turns out, in computer science especially, that when you question your assumptions, oftentimes you end up with something even better. And what the Linux kernel engineers realized is that modern CPUs are really good at copying memory, particularly memory that's been recently accessed. And so what they did is wrote in some capabilities that allow your instance and the IO domain to pre-establish a pool of memory that they both have access to all the time. And that's established when the volume is attached to your instance. When your instance wants to do an IO now, all it does is treats that pool of memory as a bounce buffer and actually copies the memory back and forth. And the amazing thing about this is we've seen significant both IOPS and latency improvements, depending on the instance type and the volumes that are going underneath it, almost double when using this method as opposed to doing TLB flushes for every single IO. Another feature that's in the 3.8 kernel is the concept of indirect grants. So instead of putting each grant that makes up that IO into the read request, what happens now is you can put those grants into one of those pages and then just include a reference in that request to that page. So your IO request can be significantly larger. Now, by default, we still allow 32 requests, and those requests are 128K maximum. And what we found is that that's a good balance between the amount of memory required and the actual performance benefits. So let's come back up a little bit, stop for a moment, do a safety stop, make sure we've shucking out the cobwebs for those of you that got a little confused. I'm going to show you a smaller example of indirect references. So this is before the 3.8 kernel. If you want to submit 128K IO, that gets broken up into 3 requests, a 44K, 2 44Ks, a 40K. Now, if you notice, that last request is not a full request. So we're actually able to put even less data into the queue. And those 3 requests each take up a slot in the queue. Now, I'm a computer scientist, so I start counting at 0. But there's 32 slots here, I promise. We only have the ability to put 9 of these 128K requests into the queue. With indirect references, that same 128K IO just takes up a single slot. So a tip, ensure you're using a kernel version that's greater than 3.8. Now, fortunately, every version of Amazon Linux, since 2003 or 2013-09, has these features enabled. Ubuntu 14.04, RHEL 7, and that also carries over to CentOS 7, also have these features enabled. Now, you don't have to be using one of these AMIs, one of these distributions. As long as you've got the 3.8 kernel or better running in your instance, you'll get the benefits of this. So as it relates to EBS, queue depth is the pending IO in flight. You need to have IO in queue in order for it to be processed by EBS. So you need to keep the EBS volume busy at all times. Now, there's no perfect queue depth. Sometimes that'll be dependent upon your application. But if you're getting the latency that you're expecting, you're probably driving enough queue depth. And what you need to understand is that once you have what you expect, you don't need to worry about this. And for some workloads, this is tunable, and I'll demonstrate that a little bit later. But the important takeaway here is that we have to have something in the queue for EBS to process it. Now, types of IOs that we have. This is a big, long chart. I don't expect you to memorize it, but it's just kind of a sample of the different types of workloads that run on AWS. Most of your database workloads are listed at the top, and they do smaller random IOs, so they're more concerned about IOPS. I've thrown Gluster on the bottom. I ran out of room, but Kafka and other things like that are larger sequential workloads. They're looking more at throughput. So our customers run a very diverse set of workloads, from e-commerce websites storing customer metadata, perhaps for your video game or whatever your e-commerce site, some big data, log analysis, things like that. To simplify the rest of this talk, I'm going to use benchmarks, and I'm specifically choosing one that represents transactional workloads. I'll be using a tool called sysbench. Some of you are probably familiar with that, with MySQL as the underlying database. Now, the choices are just random. I picked ones that I was comfortable with, but these tips that I'm about to share will apply to any of them. Now, benchmarks are great for coarse tuning. They're great for showing differences between different volume types and things like that. But really, to get the best feel for how your workload's going to perform on an EBS volume, you need to use your real-world production workload. So I picked a surprisingly common instance type and configuration to start our journey today. And I picked an M2 extra large instance. I attached a 500 gig EBS magnetic volume, and then I've run the sysbench workload a few different times. And so to show how increasing queue depth can change the number of transactions your database can do, I ran that sysbench workload a few times, increasing the number of MySQL threads, which is really increasing the queue depth to the database. Now, I don't really want to focus on specifics that may not be relevant to your particular application, but what really matters is the relative performance here. And so I've removed the values on the x and y axis, but I do want to call out a few things. This graph is linear on the y-axis, starting at 0, so it's a normal graph. I didn't play any tricks with log scale or skipping lines or anything like that. And then the x-axis, I started with 2 threads, and then I increased it to some number. And so what you'll notice is that as you're going through this, as you increase the number of threads that are writing to your volume, the transaction rate increases. Now, there's a point where that transaction rate tails off, and you're actually submitting data to the EBS volume faster than the EBS volume can process it. Now, most applications allow control over the number of concurrent operations. You should benchmark with different settings, and if you're writing your own application, ensure that you're able to handle concurrent requests to EBS. Now, you can think of this parallelism and increasing queue depth and increasing the number of threads that are writing to the MySQL or to your underlying storage, similar to the gears on my colleague's bike. All right, so now that we've taken a look at I/O, let's look at the instance and the network link. Now, I mentioned before that was a surprisingly common choice. And the M2 extra large was released in 2009 with an Intel Xeon CPU. Early last year, we released the R3 family to replace as the next generation in our high memory instance families. And so the R3 2 extra large has very similar specs to the M2 extra large. Now, don't get confused by the 2x large, 4x large differentiation. These really are equivalent to each other. The important thing to notice here, and one thing that I think is really cool, is you get better performance at 28 cents an hour less. And so that's, if you're running that instance 24/7 for an entire month, that comes out to about $200 a month. So alongside of choosing your instance, you need to choose the attributes that are important for the performance of that instance. And as it pertains to EBS, that attribute is EBS optimized. With EBS optimized instances, we allocate a separate amount of bandwidth just for your EBS traffic. And so if you're not using EBS optimized, what happens is the application, the internet, the network traffic going to your application actually shares that network with the EBS volume. And so some days you may have great performance on your EBS volume, some days you may not, and you really don't know, is it somebody driving a whole lot of load to your application, or is it your application driving load to the EBS volume, or is the EBS volume not performing well and not performing to what you need? EBS optimized instances remove some of that confusion. And now these are EBS optimized, newer generation instances are actually EBS optimized by default, and this includes our M4, C4, and D2 instance families. And the 8 extra large instances actually have a 10 gigabit network. The EBS optimized, by default, larger instances also have an additional EBS bandwidth. For the ones that have just the shared 10 gigabit network, it's a lot of traffic and a lot of room, and so it has the same caveat of a non-EBS optimized instance, but there's a lot of buffer there. And this is where you're going to get the maximum I/O and maximum IOPS from your instance. Each 8 extra large instance can support approximately 48,000 IOPS, and that's if you're doing 16K I/O. So if you're not using EBS optimized today, it's really easy to change. All you have to do is stop your instance, and that can be done either in the CLI or the console, modify the instance attribute, and restart the instance. It's pretty painless, just a little bit of downtime, just like a reboot, and it doesn't take a significant amount of time. So let's update our benchmark configuration. The only thing I've changed here is that I'm using an R3 2 extra large now. And just with that one simple change, I've gotten a 25% increase in transactions. So another example of this, and something that one of our customers, Pearson, has allowed us to do, or this has allowed them to do, recently we worked with them to switch their M1 fleet to M3s and T2s. And they saved more than 10% on their bill because of the extra performance that they could get from the newer instance types. I think that's super cool. So AWS has a few different instance families, and they have a different balance of compute, memory, some of them are mixed. But what you probably want to do is make sure that you're choosing the right instance and instance family for your workload. You're not going to want to choose a 20,000 IOPS volume and try and attach it to a T2 micro instance. You're probably not going to get the performance you're expecting. Once you've chosen that family and that right mixture of CPU and memory, to ensure the best performance, you should select the current generation of that instance family. All right, so we've talked about I/O, the instance, the network link. Let's focus on the EBS volume a little bit. So I mentioned before that EBS has a couple different volume types. They really boil down to magnetic-backed and SSD-backed volumes. Now, when you're looking at transactional workloads, you're thinking about IOPS and latency. And so for those types of workloads, you're going to want to focus on our SSD-backed. And now I lumped GP2 and PIOPS together here, mainly because the performance is very similar. It's the performance consistency that's different between the two. And so in a benchmark, you're probably not going to notice the difference between GP2 and PIOPS, but you'll notice that over time. Also, I recommend that you use a modern file system. Modern file systems tend to be journaled. They tend to handle larger volumes better and more efficiently. For example, ext4 and XFS don't actually allocate the blocks when you do the initial system call. They wait until the data is all present, and then they allocate the blocks so that your data is contained together. Other file systems, older file systems rather, do that as part of the system call. So every read request or write request, those blocks are allocated. And if you have a lot of data that's going on, they may be in different parts of your disk. Now, while there is no need to partition your volumes, just create them and attach them. If your application requires it or your operating system requires it, ensure that they're aligned on 4K boundaries. Now, when your partitions are not aligned, what happens is, SSDs are 4K page aligned. And when your partitions are not aligned, EBS has to read at least one more page to service your I/O request. And now we'll still probably deliver the IOPS that you expect. The latencies on those transactions are going to be higher. And so what does that look like? There's tools in both Windows and Linux. DiskPart is the tool in Windows that's a command line tool to manage your partitions. fdisk in Linux. So I took an EBS volume and I put 2 partitions on it. And so if you notice, the first one starts at sector 2048. It's divisible by 8, which means that it's 4K aligned. Now 8, that's a weird number. Linux shows or displays this in 512 byte sectors because that's what we advertise as the native for EBS volumes. And 8 times 512 is 4K. If you notice the second one, though, the start of that partition is offset by 2 sectors, or 1K. And so anytime I do an I/O on that partition, I'm going to have to do more work. Let's talk a little bit about pre-warming. Now, we've always discussed the need to pre-warm your volumes before you benchmark, but in most cases, it's really not necessary. How many people have tried to pre-warm a really large volume? A lot of you. You were probably in a lot of pain, weren't you? Yeah, we noticed that pre-warming large volumes took a really long time. So we've been working, and right now, I'm happy to tell you that it's no longer necessary to pre-warm a newly created volume. All you have to do is create it, attach it, mount it, and go. Your volume is going to achieve its expected performance. Now, what you might want to do, volumes restored from snapshots are a little different. We still need to get that data from S3. EBS gets that data in the background on demand. So we'll load from S3, we'll pull that data down from S3. If your I/O patterns require us to move one of those segments earlier, we'll do that. And so we've done a little bit of work to improve the performance of getting data down from S3. But if you're noticing some performance problems here and some performance issues, one of the things that you can do is read the areas of your disk to force us to load those portions and that data. Right, so one of the cool things about EBS is that we do offer a different number of volume types, and you can mix and match those volumes on your instance. And so what I've done now to our configuration, I've built upon the R32 extra large, and I've split the boot volume and the data volume. And so I've created an 8 gigabyte GP2 volume and a 500 gig GP2 volume for the data. And so just by switching from magnetic to GP2, I've increased performance 19%, or more than 50% over our original baseline. So both GP2 and PIOPS offer better performance over EBS magnetic volumes. So you should use our SSD-backed volumes when performance matters. So last year, EBS changed what we count as an I/O. We changed to 256K I/O size. And so now it's possible to be both IOPS bound and throughput bound. You can send 20,000 IOPS to an EBS volume that's provisioned with 20,000 IOPS if you're sending smaller I/Os. And if you do the math, that works out to 16K I/Os. You can also send 320 megabytes per second if you're doing larger I/Os. And so 16K is our crossover point. But if you submit 256K, you'll get 320 megabytes per second. And if you submit 4K, you'll get 20,000 IOPS. Now, if you're scratching your head about what I said before, that we've optimized in your instance and for 128K I/Os, let me explain that a little bit. In the background, if you're submitting sequential I/O, EBS will merge that I/O for you. So even if you're doing small sequential I/Os, we'll try to gather up as much of that as we can to make a 256K I/O. to give you the throughput that you're expecting. So what does this mean if you've got a smaller provisioned IOPS volume? One that may not have our full limits of 20,000 IOPS. So in this example, I'm using a volume provision with 8,000 IOPS. And I'm able to drive 8,000 IOPS, whether I'm doing 8K, 16K, or 32K, because those are all underneath our throughput limits. But what I'm not able to do is submit 16,000 IOPS, because especially if they're random, we're not going to be able to merge those, and that's beyond the capabilities of your volume. Similarly, for a throughput workload, if your I/O size is larger than we can, you can't submit 8,064 KIOs, 512 megabytes per second. Volume is only capable of 320 megabytes per second. And so in this case, what your application would see is 5,064 KIOs. But what if that's not enough? What if you need more than 16 terabytes of storage? What if you need more than 20,000 IOPS? What if you need more than 320 megabytes per second? Well, one of the things that you can do within your instance is you can RAID. And when we talk about RAID, we're usually talking about RAID 0, increasing capacity, or performance. Rarely we want to talk about redundancy. Let's take a moment to dive into that. When you do a RAID 1 or a mirror within your instance, every write that you write to your EBS volume has to be written twice. And so you're going to effectively have the bandwidth of your EBS optimized instance. Now, EBS already has a durability that's greater than a hard drive. If that's not good enough for you, what we recommend is that you do application level redundancy, and even better if you're doing that to a different availability zone. It'll give you a more available service. The other important thing to remember is that when you're striping volumes together, you don't want to mix volume types. You don't want to create a RAID set with 6 magnetic volumes and 3 GP2 volumes. You're probably not going to get the performance you're expecting out of that. Your performance is going to look more like the magnetic volume than it does the GP2 volume. When you do stripe a volume, you need to take some special attention when you're taking snapshots. And so for a database, you're going to want to flush and lock your tables. The file system, you might be able to sync or freeze, and then you can do the snapshot of all the volumes together. And this will give you a point-in-time snapshot. Now, when that snapshot API call returns, the create snapshot API returns, that means that it's safe to resume I/O. We've recorded all of the data that we need to record to complete those snapshots. Now, many journal file systems and databases will work without this. But what I really want you to do, if you're going to rely on that, I want you to test it before you rely on it in a failure scenario. I don't want you to be sad. So let's revisit our system. We've optimized everything. We've got the right EC2 instance with enough EBS optimized bandwidth, the right EBS volumes, and our application is tuned to drive a bunch of I/O. And so we've got a nice balanced system. We've maximized EC2 and EBS performance. How do we ensure that we maintain this performance? And so one of the things that we've got within Amazon is our CloudWatch service. Now, if you're not using CloudWatch today, I highly recommend it. CloudWatch provides metrics for all AWS services, and EBS is no different. You can take a look at the metrics for your volume, determine if your volume or volumes are performing as expected. A tip here, all the EBS metrics are prefixed with the word volume. So there's some metrics in there that are related to your instance that say disk I/O and disk read write. Those are actually your local instance storage and not your EBS volumes. So to show you what it looks like when you're exceeding the EBS optimized limits of your instance, I've taken the same 2,000 PIOPS volume and attached it to 3 different instances. The first line, you'll notice that I'm only getting 128 megabytes per second. That's because I attached it to an M4 2 extra large, and that's all the EBS optimized bandwidth that that instance type supports. Now I bumped up the size to an M4 4 extra large, and I'm still getting great performance. I'm just still limited by that instance, 256 megabytes per second. If I go all the way up to an M4 10x large, I'm getting the capabilities of the volume. And the M410X Large actually has even more capability if you wanted to attach more volumes to it. Now, CloudWatch metrics are provided on all EBS volumes. For provisioned IOPS volumes, they're provided at a 1-minute granularity, and for everything else, they're a 5-minute granularity, and those are free within your CloudWatch console. But if CloudWatch isn't enough, if you need something more frequently, there's a number of tools that you can use to even monitor the performance a little bit more granular. IOStat is one of them in Linux, and here I've shown an example on 1-second boundaries. And it's important to remember with IOStat, that very first line that it shows you is going to be an average of that volume's performance since the instance booted. So it's not a snapshot in time. IOStat provides a lot of information about how many requests are merged, how many requests your application is submitting, the queue depth, the average await is the latency, and then the average request size. Now, the important thing to remember with parallel storage systems is that utilization and service time don't mean what you think they mean. Utilization is actually the amount of time the device spent servicing at least one I/O. There's no bonus points in utilization for submitting 2 I/Os or 3 I/Os. So it doesn't really tell you about the capabilities of your volume. It just tells you how active your volume is. And the other thing with service time is it really doesn't do a good job of taking parallelism into account. If you're submitting 10 I/Os all at the same time, and they complete 1 millisecond later, service time is going to report that they each took 100 microseconds. Not really reality. So within your Windows instance, for anybody that's using Windows, there's a tool called perfmon. And backing up perfmon, it provides about the same amount of data as IOStat. The Windows performance gathering metrics system feeds data into here, and you're actually able to extract the raw data from perfmon as well. So if you want to do different slicing and dicing on it, more than perfmon can do, that's available to you as well. So really the important things here are to select the right instance for your workload. Don't take that T2 micro and attach a 20,000 PIOPS volume to it. Select the right volume for your workload. If you're concerned about latency and IOPS, you might want to consider an SSD-backed volume. Increase the parallelism of I/O, and make sure that your volume and your whole system is performing as you expected by monitoring with CloudWatch. Now for another deep dive, tomorrow there's a talk about Amazon EBS and Cassandra. This is specific to Cassandra and shows how CrowdStrike was able to get 1 million writes per second using EBS volumes on 60 nodes. So I've got some friends from EBS, and we're happy to take some questions one-on-one after this session, but thank you all for attending today, and hopefully this was helpful.